All right, so we are now in Excel, and we're just going to talk through how do we make a stress strain diagram. So, first off, the keyboard here should light up as I type things. I know Excel can be really annoying to try to follow what someone's doing, so the hope is that you can actually see my keystrokes a little bit. Um, but we are given info on what's the load that our specimen has and its elongation at a handful of different loads. We also know what the gauge length was and its diameter. If we were actually doing this, really this info right here, that given info, is what we'd start out knowing. We'd load it up and start testing the specimen, and we gather all of this data. As we go along, what we're trying to get to is what's our or we're calculated out what's our strain and what's our stress. And Excel's going to play nicer with us if we set this up so that um, we put in strain first, and I'm in millimeters for my elongation, so millimeters per millimeter, and then I can put in what's the stress that we're working with. Which if I'm in SI units, I probably want megapascals coming out. So we'll set that up. I know to get strain, I need a delta L over L. So my delta L will be that elongation. The length will be my gauge length. So I can actually come in and set that one up right now. This equals, we'll just go elongation, delta L over gauge length. And I want, as I drag this down, I'll be able to reference every cell right next to it, or I'll update that formula. If I do this as is, as I come down with that, let's go down like 3, and it's going to start giving us problems in here. And really what's happening is, without like any reference in here, Excel's just going to update. If I go down one cell, it will still reference 1 to the left and 1, 2, 3, 4, 5, 6, 7, 8, 9, or 8 or 9 over. I want it to always reference this 50 millimeters though. So I don't want to do just dragging it down. I always want to reference one cell to the left. So I'm going to leave that D7 as is, but I want to always get that B52, 50 millimeters in there. So we can come in and just put dollar signs. Dollar signs in front of B, dollar signs in front of the 2. That way it always is going to reference that specific cell for us. You can also get that if you hit F4 when you are selecting a cell, it will do the same thing. But now if I come in and I hover over until my cursor turns black there and go down with it or double click, it's going to keep referencing one cell to the left and 50, which again is exactly what we want there. The one error we get is down here at the end. Excel doesn't know what to do with like fracture divided by 50, so it's telling us there's a problem. And we'll just delete that one out. We don't need to know what's happening there. There realistically isn't a strain if we've broken the thing in half. But then we can come in and get the stress out for everything. For stress, we can do, well, stress is a force divided by an area. If I'm looking for that, I need to know what my cross-sectional area is. So let's actually add one more calculation over here. What's my area in millimeters squared? And I can get that using another formula. Area for a circle, if I have a diameter, I'm circular, should be pi times the radius squared, or pi times diameter squared, over 4. So let's go ahead and tackle that. Equals, for pi, we can type in pi, open and close parentheses, gets us exactly pi. So we don't need to round that off. Excel has pi built in. But times our diameter, we square the diameter, so caret 2 divided by 4, over 4. And we get our cross-sectional area is 399.73 square millimeters, which we can use in our P over A equation. So come back to our stress and start making a formula here. Equals, we want to take our load divided by that area. The one thing we want to catch in here, if I'm trying to get to megapascals, I want newtons per square millimeter. So I have to do a quick unit conversion in here. To get kilonewtons to newtons, I just multiply by 1,000. Times 1,000 divided by my area. And we get no stress, which makes sense. I haven't put any load on yet. I haven't elongated. There's no strain. There's no stress. But from there, I want to always reference that area. So again, let's stick dollar signs on this. Dollar sign B, dollar sign 4. But I should always reference 1, 2, 3 cells to the left. So as I drag that down, it selects everything in this column and gets this calculated outright. So going down with that, we're gonna get that for our stress. Calculated strain, calculated stress. We're good to come in and make our plots. So I'm gonna highlight both of my columns in here and come in and say I want to go to insert and we want a scatter plot, which is this one right here. If I hover over it, there should be a thing that pops up and says it's the XY scatter. So we can click that one. And what I typically use is, I always talk through what the options are. One of these just shows every data point in here. One shows the data points and connects them with nice smooth lines. One hides the data points but shows the smooth lines. One gets straight lines and all the data points, and then straight lines without data points. I typically use the one that shows the data points and the smooth lines. Every once in a while I do something different. But if I click on that, it'll pull up my stress strain diagram. We're going to make a couple changes in here. For example, Excel tries to be helpful and tell us this is the stress in megapascals. It's just pulling headers off of my table in here. This is really our stress strain diagram. One other thing we should do is we always want to label our axes. So that x-axis in here is the strain. So if I come into my table and come up to the top left, there's an add chart element, and I can add a primary horizontal and a primary vertical axis. Then we can come in and fill those in. That horizontal axis is our strain in millimeters per millimeter. And that vertical axis should be our stress. I got one S in there. Stress in megapascals. That's really the key thing. That is our stress strain diagram. There's one other thing we want to do though. We can read some of our values off of this. What's our fracture stress? What's our ultimate stress? But one thing that'd be really hard to do is look at this and figure out what's the slope. What's Young's modulus? So if we're trying to tackle that, I would copy and paste this chart. So just Command C or Control C, Control V, and then come in and rather than plotting every data point, let's just unselect a bunch. So if I click in here on my line, I can come back into my data and just grab the corner and drag up. And let's go to let's try this. So right here, we get a linear line and then it turns and I have 1, 2, 3 pieces that are definitely past the linear section. Let's go up a little bit farther. So 1, 2, I don't want to go 1 or 2 points past that. But if I have this, I'll update my title in here. This is the linear portion of the stress strain diagram. But that's going to get us a way easier chart to come in and try to read what is our Young's modulus off of. And we could come in with more advanced time. We could try to add in more fine scales in here so we could get more precise numbers off of that. But really what I'm trying to figure out is where does it look like it stops being linear? And it's probably right here just above 70. So if I were trying to figure out Young's modulus, I would do rise over run. So my change in stress would be 71.29 minus 0 divided by my change in strain, 0.0016 minus 0. And we get E out from that. Just rise over run is the slope of a constant straight line. But that's really all we're shooting to get through for this one. Hopefully that was useful for us. If it was, hit those like and subscribe buttons. Let's get you in A with JJ.